All right, this portion of the course we're going to be concerned with spontaneous and non-spontaneous processes. A spontaneous process occurs naturally under a given set of conditions, and a non-spontaneous process does not. A non-spontaneous process is going to require some intervention from outside forces for it to be able to occur. Now, it is crucial to not confuse spontaneity with rapidity. Just because a reaction is spontaneous doesn't mean the reaction is going to occur quickly or observably to our eyes. For example, carbon going to diamond. These are both forms of elemental carbon, two different allotropes. We can see the atoms are connected differently. We could determine the value of delta G for this reaction, the Gibbs free energy. We would find it was less than 0, which we will learn means that this reaction is spontaneous. However, the reaction is immeasurably slow at normal room conditions. It would take millions of years. So just because it's spontaneous doesn't mean that it would be observable to our eyes in a reasonable time frame. Now, if we look at a spontaneous reaction, a reaction that's spontaneous in the forward reaction is going to be non-spontaneous in the reverse direction. In the next portion of the course, we're going to be considering spontaneity. First, we'll consider the role of enthalpy or heat energy in spontaneity. Spontaneous reactions are often exothermic, but not always exothermic. In this first example, we see a reaction that's not exothermic, but yet is spontaneous. A gas is contained in a single bulb connected to an evacuated bulb. If we open the valve, the spontaneous reaction is the gas rushing into the second bulb and achieving a state where there's equal distribution of gas particles across both bulbs. If we look at the heat arguments, we see the work is equal to 0 because this is free expansion. And if we have an ideal gas, delta H is equal to 0. So even though this is a spontaneous reaction, it's not exothermic. In the second example, we see a hot object and a cooler object. So when they come in thermal contact, heat spontaneously is distributed equally across both objects. Overall, there is no change in heat energy. This is all leading to say that there's some factor other than energy. In this case, we're considering heat energy. There's some other factor that's important to the spontaneity of the process. And if we look at both these examples, we see that there's a consistency in that a greater, more uniform dispersal of matter or energy or energy can be the driving force of a spontaneous process. This factor is termed entropy. All right, so let's think about enthalpy and spontaneity, heat energy and spontaneity. We will notice that spontaneous reactions are often exothermic, but there are some situations where they're not exothermic. Two examples follow. In this first example, we have gas that's being held in a bulb at some pressure connected to an evacuated bulb. If we open the stopcock, spontaneously gas particles will redistribute themselves such that there's approximately equal distribution in both bulbs. Now the delta H for this process is equal to 0 if we're considering the gases to be ideal. We know that work is going to be equal to the negative integral of P dV, and that is going to be equal to 0 for a free expansion. In this second example, we have a hot object and a cooler object. When these objects are placed in thermal contact, heat energy is going to spontaneously redistribute itself across both of these objects equally. The net heat energy is unchanged. There is no change in the total amount of heat energy. The energy is simply distributed differently or uniformly now across both objects. Both of these examples go to demonstrate that some factor other than heat energy is important to the spontaneity of the process. And if we look at both of these processes, you'll see the spontaneous reaction is in the direction that results in a more uniform distribution of matter or a more uniform distribution of energy. We're going to see this type of process in terms of a factor called entropy.